Hi, I'm John Watt, and welcome to Ever Wondered, the show that takes you behind the scenes to look at what has been achieved at the cutting edge of science and technology right here in New Zealand. This week, our journey takes us beyond the terrestrial realm into the wonders of space and the mysteries of the universe, and what Kiwi scientists are doing to unravel them. I'm here in Tekapa at the Mount John Observatory to meet Professor John Hernshaw, a scientist who's using the subtle shift in a star's position to discover distant planets similar to our own.
My name is John Hernshaw and I'm Professor of Astronomy at the University of Canterbury. One thing I'm very interested in is the business of trying to find planets orbiting other stars. The first planet orbiting another star was found in 1995, so it's fairly recently.
That planet orbits a star known as 51 Pegasi, located near the constellation of Pegasus, and is almost 51 light years away from Earth. Since then, hundreds more have been found.
Most of these planets already discovered are planets like Jupiter, what we call gas giants. The real challenge now is to find planets like the Earth, which are much smaller than Jupiter, and they have rocky surfaces.
And what a challenge it is. Extrasolar planets are so far away, they are impossible to observe directly. So instead, astronomers use the light of the star that the planet orbits around to confirm the planet's presence. There are three methods used, and we're going to look at one: radial velocity, also known as the Doppler method.
Planets are incredibly hard to find because here's a star and here's a planet. The light from that planet may be 1 billion times fainter than the star. What we can do is find the kind of reflex motion of a star when a planet orbits it. There's a planet orbiting a star. Mind out or I'll hit you in the head. What you notice is the star is not actually stationary, the star is wobbling. You're the observer. Sometimes the star is coming towards you, sometimes away from you.
Okay, I can see.
And if we see a star wobbling like that, then we can infer there must be something orbiting it, something dark we can't see.
But as the mass of the planet gets smaller and smaller relative to the mass of the star, this backwards and forwards motion becomes very difficult to detect. It can be as small as a 10 centimetre movement for an Earth-sized planet. So what do we need this beast for?
It's a signal generator. It's going to put out a sound wave of one pitch or frequency. There we have a frequency of 800 hertz. So imagine this is a star putting out light. It's also wobbling. When this is coming towards you, you hear a slightly higher frequency than 800 cycles per second. When it's going away, you hear a slightly lower frequency, do you?
Yeah.
I can't detect it because the distance between me and the loudspeaker is constant. There's no variable velocity from my perspective.
But to me, it's shifting around.
Really? Good.
Light does the same thing, but 1 million times less shift in frequency, so it's much harder to detect. Using the Doppler method, when a star wobbles away from us, the frequency of the light gets lower, and we get a tiny red shift. When the star wobbles towards us, the frequency of the light increases, and you get a tiny blue shift.
What you're looking at now is our 1 metre telescope.
This is the telescope?
Yeah, and we built this ourselves in the 1980s.
This is built in New Zealand?
At the University of Canterbury.
And how much does this thing weigh? It's gigantic.
I don't know exactly, it's probably a ton or so.
Like a truck.
Yeah. So the whole telescope's perfectly balanced. You can actually move it with one finger if you turn off the motors and just push it.
So up we go to have a look at this precision instrument.
Reflecting telescopes use mirrors, not lenses. There's a large mirror here, it's a concave mirror, and the parallel light rays from a star reflect off that mirror, and they are converging towards a second mirror, a convex mirror, and then after reflection from that mirror, they go down this great big cylindrical pipe. And that's where the optical fibre starts. Now this is the optical fibre.
Okay.
So starlight travels through that fibre, it's just the width of a human hair, and it travels about 25 metres into the spectrograph. So this is the Hercules spectrograph, which we designed and built at the University of Canterbury.
So this is measuring the light that comes through the telescope?
Yes, it's splitting the light up into its component colours. We are measuring the colour, or wavelength as we call it, of light. The whole instrument's in a great big vacuum tank, and if it travels through a vacuum, we know that the wavelength can't be altered at all by the air around it.
Dusk is falling, and it's a perfect night for looking at the stars. John takes advantage of this clear, frosty evening in Tekapo, and we put the telescope through its paces.
You know, the people who live in cities often never get to see the wonderful starry heavens. But here at Tekapo, the sky is so dark we can see thousands of stars. That's great.
With starlight coming through the spectrograph, John shows me how he analyses the incoming data.
So we are not recording images of stars as such, but we're recording images of the spectra of stars. So it's showing the intensity of starlight for every different colour. So that's the light from the star being spread out into a strip. A great big, long, thin spectrum has been sliced up into what we call orders, and each order contains about 4,000 detectable wavelengths. So overall, there's about 500,000 different wavelength positions. Stars have what we call absorption lines, where light is missing.
Right.
And can you see those there and there?
Tiny little holes in the line.
Now, these are due to sodium atoms in the star itself.
So this is telling you what the star has inside it.
You can actually measure not only how fast stars are moving, which is what we were talking about before, but actually what stars are made out of.
Sodium's like in your street lamp, so this is the same kind of colour that you get in your street lamp, but coming from a star.
How precisely can you measure the velocity of a wobbling star? And at present, the best observations in the world are a few metres per second. For an Earth-like planet, the wobble would only be 10 centimetres per second. You can't visualise how precisely one has to measure velocity, something which has never been done before for stars.
Looking for a 10-centimetre movement in a star billions of kilometres away may seem almost impossible, but John is confident it's only a matter of time before the Doppler method provides real results in the search for Earth-like planets.
Finding planets is the most exciting branch of astronomy at the present time. New Zealand does a few branches of astronomy, but does them extremely well. So I think we can compete on the world stage, and some things we do as well as, or even better, than anywhere else.
To date, optical astronomy has been the dominant method for understanding the workings of the universe, but it's possible to explore even further and deeper. We're going to have a look at radio astronomy, a field of astrophysics that uses invisible waves to explore deep into the cosmos.
My name is Melanie Johnston-Hollett. I'm a senior lecturer at the Victoria University of Wellington, and I'm the leader of the Radio Astronomy Research Group. All astronomy is kind of like being an archaeologist for the universe. Because light travels at a finite speed, it means that when light comes to us, it's travelled a large distance, and that means necessarily that it's come from a long, long, long time ago. Well, if you're looking back in time, then what you're doing is essentially you're probing the evolutionary record, if you like, of galaxies in the universe. So we can do projects like understand how galaxies evolved over cosmic time. So I work on magnetic fields, and I also work on large-scale structure in the universe and trying to understand how structure forms. In particular, we look at something called galaxy clusters, which are groupings of hundreds to thousands of galaxies, and how the environment around those galaxies affects their life cycle. You get groups of galaxies embedded in hot gas which is a million to 10 million degrees, smashing into each other, and this produces events which are the most energetic things since the Big Bang. So you get shock waves travelling out in the universe. If you want to look for these particular shock waves, then one of the ways that you can do it is you get a radio telescope and you look for the radio emission which is produced in the shock wave when electrons, which are travelling very close to the speed of light, are accelerated as the shock compresses a magnetic field in front of them, and that lights up in the radio like a beacon. So we can actually find this sort of cosmic wreckage, if you like, with a radio telescope. Okay, so what we're looking at here is this is the control software for the Australia Telescope Compact Array, which is the array in New South Wales. Right. So this is what it looks like at the moment. It's in what's called a compact configuration, so there's 6 antennas. What we're actually looking at here, which is a galaxy cluster, has got lots of structure, and that's good because we're looking for stuff which is large. Okay. So that's cool.
What are all the small points?
They're individual galaxies. Okay. So yeah, an individual galaxy is about that big in this image. So you can see that these shockwaves are really many times larger than a galaxy.
Radio waves are part of the same electromagnetic spectrum as visible light waves, but they allow us to look further and deeper into the universe.
These things that we're looking at are very hard to detect, and there's only about 30 odd clusters known where we see this signature. And if you want to see what's called double relics, where you see a forward shock and a backward shock, we only know those in 5 objects. We're excited because Sarah's just discovered another one, so we've now got 6, you see.
Sick.
Yeah.
The double relic is so rare that only 5 have previously been discovered. Sarah Shakuri, a PhD student at Victoria University, has just discovered the 6th.
This is the center of the cluster, and this radio relic here, it is occurring in the edge of the cluster. The second relic we have discovered is occurring in this other edge.
To make these kinds of discoveries, you need large, very precise telescopes. So let's go and have a look at one. I'm here in Warkworth with Sergei Gulyev and Tim Natush from AUT to get an up-close look at this precision instrument.
I'm Tim Natush. I have the good fortune to work for AUT and the Institute for Radio Astronomy and Space Research.
My name is Sergei Gulyev. I'm director of Research Institute for Radio Astronomy and Space Research. A radio wave comes to this main reflector. It's a paraboloid, and then it reflects towards that hyperbola, that secondary reflector, secondary mirror, and then back to the feed horn. You need to have a pretty accurate surface. Believe me or not, the quality of this surface is very high. It is 0.3 millimeter.
Whoa, so this 12-meter curved dish has to be accurate to 0.3 of a millimeter over its entire surface. So Tim, how was it built?
Well, out of a giant kit of parts. I mean, we had 2 40-foot containers that were delivered to site, and this whole structure was in thousands of pieces.
So it's like a kit set.
It was like a kit set, essentially. The ribs are bolted to the hub, the surface plates are put on, and then backing plates are put on underneath to actually tie the whole structure together.
Now imagine not one radio telescope, but thousands of radio telescopes, all linked together and working as one powerful instrument. Welcome to the SKA, the Square Kilometre Array.
The SKA is a proposal for the world's biggest ever radio telescope. Size matters. The bigger the telescope, the better the sensitivity, the weaker the sources we can look at, and also the finer the detail of the images that we can actually produce of these objects.
This telescope will combine power of thousands of dishes, like this AUT radio telescope. It's a prototype of SK dishes.
This ambitious scheme will link thousands of separate dishes spread out over the size of a continent to make one giant virtual dish the size of 1 square kilometre.
All of them will be interconnected, and information will go to the central supercomputer.
The supercomputer that we need to actually correlate the signals or to bring them together and make sense of them is something which does not yet exist. And it's a machine which would need to be able to deal with data of the order of exabytes per day.
Exa is actually billion operations per second in computer.
So what that means is the SKA will collect in one day more data than has ever been spoken by humans in our entire history.
So what could this mean for us?
With the help of SKA, we'll be able to answer fundamental questions.
And it really will allow us to get to the bottom of some of these mysteries. The operation of the black holes at the center of active galactic nuclei and quasars, the search for the origins of the magnetism that we see in galaxies.
It will give us fantastic boost in terms of industry technology.
So where does New Zealand fit into this mega project?
It originally started off with some 5, 6, 7 different countries bidding to host the instrument. Currently, there are just 2 locations left in the running: South Africa, and then a combined bid from Australia and New Zealand. So there's a bit of a race on here now to attract the eyes of the international community and to hopefully nail the bid for New Zealand and Australia.
It is a big deal. It's a huge deal for us to be involved in that. It is one of the most truly remarkable and exciting astronomy projects to come along in the next decade, and being able to participate in that really allows New Zealand scientists to get involved in cutting-edge global science.
If New Zealand is successful in its bid to become a part of the SKA, then Kiwi science could be instrumental in uncovering some of the universe's deepest secrets. From observing space to travelling through space, we're off to meet scientist Susan Krumdijk at the University of Canterbury, who's been asked by NASA to help create their next generation of hypersonic spacecraft.
I'm Susan Krumdijk, and I'm an associate professor in mechanical engineering at University of Canterbury. NASA contacted me about being part of this hypersonic vehicle research. So we're talking about vehicles that are hypersonic. You know, we're talking 10 times the speed of sound and more. And so that's ridiculously fast if you think about it, 8,000 kilometers an hour. What if we had a vehicle that could go Mach 10 to Mach 15? What would it have to be like? What materials would it have to be made out of? How would you control it? Because you're going so fast that by the time you even sent a control signal, it'd be too late. So how would such a thing work? You would know that it would have to survive really high temperatures because it's moving so fast through the air that the heating on the outside is enormous, 1,500 to 2,000 degrees. So that's too hot for any kind of metal, really. So we can't make it out of metal. Ceramic materials are the only things that are going to survive those temperatures and stresses. But ceramics are, you know, like glass and teacups and things like that. So it's got to be some sort of new ceramic. But it also has to be a ceramic that's flexible. The silicon carbide composites is the target at the moment. So you got a huge amount of strength, and you take those fibers and weave them into a shape where you can use that strength. So the weavers then, essentially like knitting a big sock, they knit the plane. That little bit of a weave on the surface isn't acceptable. It's going to have to be glassy smooth so that it can slice through the air. And that's where the exterior coatings come in.
Susan's mission is to formulate the right chemical combination in order to create a smooth and heat-resistant coating.
So there's actually 2 layers that I'm working on. One is a way to put down a polymer ceramic. Now, usually ceramic is crystalline. Say quartz, that's a silicon and oxygen crystal. But to get a very smooth shape, we're going to need to have a polymer. So if you think about plastic, you can make real smooth things out of plastic. And this is a very strange and interesting thing, the polymer ceramic. And then on top of that goes another ceramic, which we do want to be crystalline because it'll resist the oxygen attack and be a thermal coating.
Susan's next problem is how to apply this special coating evenly across the entire surface of the craft.
I'm going to use a method which is called chemical vapor deposition. And what it means is that you take some chemicals, and if you get those into a vapor form around an object that you've heated up, a chemical reaction will happen on the surface and leave behind the ceramic crystals. So you can see that we've put in a 3-dimensional object there. It's a little rod, a little metal rod.
Tiny,
right.
Rod.
And there's a heater below that rod, which is going to get quite hot, about 600 degrees.
600?
And that's going to heat the rod. You sort of make a little package, a little chemical package that has everything ready to deliver. You've got your metal atom and you've got your oxygen atoms, and they're wrapped up in a package of hydrocarbons. And when that little package gets hot enough, it unzips and leaves behind your ceramic. And then if I were to spray the precursor chemical that's in a liquid form into a vacuum, what would happen to it? It hasn't any choice. It has to become a gas. It has to vaporize, has to evaporate. What is going to happen to it? Where's it going to go? When you have a material and a huge pressure difference, it has to expand to fill that void. And if I've put my object in that vacuum chamber, it's going to have to fill that all around the thing, which is going to make a coating all over it.
As the chemicals form a coating over the hot metal rod, you can see it change colour over time. This coating, just one of many to be put to the test, is taken away for closer analysis.
You do have to really like to get into the science, to go into the scanning electron microscope and look at what you did and see what shape the crystals are and try and figure out why was that? Was it because we had a higher temperature? Was it because we were putting in more material? And just, figure out how it's working. We don't really know exactly what ratios of those materials together or what kinds of crystals are going to give us the best performance there. So that's where we move right into the material science. It's just pure material science. Here's a crystal, and now we're going to test it and probe it and hit it with oxygen ions and put it in a furnace and look at its X-ray diffraction pattern. We're going to do all this materials analysis on it and just try and learn what it does. If you're going to work on that kind of science, it doesn't have a 2-year time frame. It has a continuous time frame. There are reasons to work on things that really don't have a due date, where you're just driving in a direction that you wouldn't have otherwise gone just because it pushes the science into places it hasn't gone before.
These projects show the trend towards collaborative global research, with Kiwi scientists right at the heart of some of the world's most exciting and complex research initiatives. That's all for this week of Ever Wondered. See you again next time.